So we all know climate change is ramping up the intensity and frequency of floods. And for conservationists, that raises a huge question. How is this affecting wildlife? Well, a really fascinating new study in ecological indicators offers an innovative way to get ahead of this. It's not just about understanding the threat after the fact, but actually predicting it, giving us a powerful new tool to protect vulnerable species.
All right, so here's how we're going to break this down. First, we'll look at the problem with floods in our current models. Then we'll get into the novel research question they asked. We'll cover how they mapped flood susceptibility, how that improved biodiversity models, and, of course, the key findings. And we'll wrap up with the implications and what this means for the future.
Okay, so let's start with the core challenge. We all know floods are a huge deal. They can completely reshape an ecosystem. But the thing is, our standard tools for predicting where species might live, well, they've always struggled to deal with something as chaotic and unpredictable as a flood.
Right, so these tools are called species distribution models, or SDMs for short. Now, if you're not in this field every day, you can just think of them as ecological forecasting models. They take really stable data, things like average temperature or annual rainfall, and use it to map out where a species can likely survive. But here's the catch. A flood isn't a stable variable. It's a sudden, disruptive event, and that has created this huge blind spot in how we model biodiversity.
And this is where the research gets really, really clever. The scientists behind this study proposed a fundamental shift in how we think about this problem. Instead of trying to model the chaos of individual, unpredictable floods, they decided to ask a completely different question.
And here it is. This is really the aha moment of the whole paper. They asked, instead of modeling unpredictable flood events, what if we model an area's underlying susceptibility to floods? Think about it. The things that make a place likely to flood, like its slope, the type of soil, how close it is to a river, those things are pretty stable. They don't just change overnight. So they create this consistent, mappable level of vulnerability. This simple shift reframes the entire problem into a really clean, testable scientific question. So the big question becomes, if we create a map of this underlying flood susceptibility and add it as a new variable, can it significantly improve the accuracy of our species distribution models?
And this is what's so cool about this research. This isn't just a small tweak to an existing method. This is the very first study to formally test this innovative approach. It's truly pioneering work.
Okay, so how did they actually do it? How do you build a map of something like flood susceptibility? Let's dive into the methodology. It's a really impressive mix of satellite data, environmental factors, and some pretty sophisticated machine learning. Now, this flowchart from the paper gives you the bird's eye view of the whole process. I know, it looks a little complex at first glance, but it's actually pretty logical when you break it down. Over on the left, you have all your data inputs, satellite images, topography, climate info. That all gets fed into the middle, where the machine learning magic happens to create the flood susceptibility model. And then, on the right, they take that new model and plug it into the species data to see if it makes a difference. Let's walk through the key steps. So it really boils down to three main steps. First, they had to figure out where floods actually happened. To do that, they used 7 years of satellite radar images. Step 2, they identified 9 key environmental factors that make a place likely to flood. Stuff like the steepness of the terrain, precipitation patterns, even the type of vegetation. And finally, step 3, they used machine learning to connect the dots, linking those environmental factors to the real-world flood locations to create their final susceptibility map. This image is a perfect illustration of that first step. They use data from the Sentinel-1 satellite, which uses something called synthetic aperture radar, or SAR. And SAR is amazing because it can see right through clouds, day or night. So by comparing an image taken before a big storm to one taken after, the computer can spot the differences and say, aha, that's new water on the ground. It's an incredibly powerful way to map actual flood zones. And here it is. This is the final product of all that work. This is their detailed flood susceptibility map for the Zagros Mountains in Iran, which is a really important biodiversity hotspot. You can see it right there. The dark blue zones are the areas the model has flagged as having the highest underlying risk of flooding, based on all those landscape features we just talked about. Okay, so they've built this amazing new map, but now comes the moment of truth. Does it actually make a difference? Does it work? To figure that out, they designed a really clear head-to-head test. Here's what they did. They looked at 34 different species in the area, mammals, reptiles, and amphibians. And for every single one of those species, they ran 2 different models. The first model was the climate-only version. Think of this as the standard business-as-usual approach. The second was the climate flood model. Here they took out one of the climate variables and swapped in their brand new flood susceptibility map. It was a classic bake-off to see which one performed better. All right, we've gone through the setup, we've seen the methodology, so what happened? What did the data actually reveal? Did adding the flood map work? Well, the results were pretty unambiguous. In fact, you can almost boil the main takeaway down to a single number: 67%. So what is that? That's the percentage of species where the model that included the flood map was significantly more accurate than the one that didn't. We're talking about 2/3 of all the species they tested. This wasn't just a tiny improvement, this was a really big deal.
And you can literally see the difference it makes. On the left, you've got the prediction for species richness. That's basically just the number of different species using only the standard climate model. The predicted hotspots are, well, they're pretty broad. Now look at the map on the right. This is the one that includes the flood risk data. See how much more precise and constrained it is? It's a much more realistic picture. It shows us that these high-risk flood zones are a real limiting factor, helping us zero in on where the true biodiversity hotspots are.
And another fascinating detail they found is that not all animals are affected in the same way. The models showed that the negative impact of flood risk was by far the strongest for amphibians. And that makes a ton of sense, right? Their life cycles are so tied to water conditions. Mammals were in the middle, and reptiles seem to be the least affected, which again might be because they're better equipped to handle those kinds of wet conditions.
Okay, so this is all great science, but what does it actually mean on the ground? Why does this matter? Well, this goes way beyond just being an interesting academic paper. It has some serious real-world implications for conservation.
What this really does is give conservation planners a much, much sharper tool. You can now overlay a map of high biodiversity with this new map of high flood risk. Suddenly, you can pinpoint the exact areas that are both incredibly valuable and incredibly vulnerable. And that is absolutely crucial for prioritizing action. It helps us figure out where to focus our limited time and money, whether it's for protection, for habitat restoration, or for building resilience against future climate threats.
And this leaves us with a really powerful final thought. What this study has given us is a new template, a new way of thinking. They took a chaotic, unpredictable event, a flood, and figured out how to model its stable underlying susceptibility. So the big question is, if this works for floods, what else could it work for? Could we use this same approach to model things like fire risk, or landslide vulnerability, or drought susceptibility? Imagine if we could get ahead of all these threats to better protect the world's biodiversity.